This week's lab is a qualitative exploration of hydrocarbons. We're going to look at three classifications of hydrocarbon. They are alkanes. Alkanes are saturated hydrocarbons, contain only carbon-to-carbon single bonds, and then terminal carbon-to-hydrogen single bonds also. And the molecule that we'll be using as a representative of that subset is cyclohexane. We'll look at alkenes. Alkenes are unsaturated hydrocarbons. They contain a carbon-to-carbon double bond, and we'll be looking at cyclohexene. Aromatics are a special kind of unsaturated hydrocarbon, special in that they have a pi system that runs double bond, single bond, double bond, single bond, double bond, single bond in a cyclic system. This is a very stabilizing arrangement of electrons, and so when we look at reactivity, what we're expecting, there's no polar groups here, there's no concentration of electrons. So we expect that alkanes will not react with acids, nor will they react with bases. Alkanes are, by and large, unreactive. Alkenes, however, have a concentration of electrons right here. They're going to react by addition. They're going to add groups across this double bond. Aromatics don't want to add across the double bond and lose the special stabilization that is aromaticity in this ring. So they're going to react by substitution instead. We're not anticipating any of the reagents causing a reaction with the alkanes. We do, however, anticipate that the alkenes will react in a couple of these cases. Alkene plus bromine, either in tetrachloromethane or in water, is brown, colorless molecule plus brown reagent. The bromines will add across that original double bond, making a colorless material, meaning that as this reaction progresses, the yellow-brown color in your test tube will go away. Dissipation of that color is a positive test for an alkene. With potassium permanganate, which is an intense purple color, expect an alkene to add two alcohol groups across that original double bond. Again, your purple color goes away, but this time it's replaced by the brown color of manganese 4 oxide. This is manganese in the +7 oxidation state, manganese in the +4. They're different colors. Alkenes react with concentrated sulfuric acid, not dilute. Dilute sulfuric acid gives a completely different reaction, but concentrated sulfuric acid makes a alkyl sulfate, and we're seeing an orangey brown coloration with this, possibly due to over dehydration of the reagents. We're only expecting one reaction from the aromatic molecule, and that will be this one, the toluene, which is a colorless liquid that is insoluble in water. Hydrocarbons and water, not soluble. When you react it with concentrated sulfuric acid, makes the sulfonic acid, the sulfonyl toluene, and this is a colorless liquid that is soluble in water. So at the start of the reaction, you will see two layers in the test tube, organic layer, water layer. As the reaction progresses, you should see a single layer at the end of the reaction. We've set up test tubes to do two banks of qualitative tests. Here, an alkane, an alkene, and an aromatic material have been added to the bottom of a test tube. Now we're going to add just a couple of drops of potassium permanganate. You can see that it is purple. give those a little shake and wait a couple of minutes. Next, we'll do the same thing. We'll add just a couple of drops of bromine water to the small number of drops of hydrocarbon that is in each test tube. Let's look at the outcome of this first battery of tests. If we inspect the alkane plus bromine water, what we can see is that there are two layers at the bottom of the test tube. All hydrocarbons are less dense than water. If you can see any yellow tinge still in the test tube from the bromine water, then the bromine has not been taken up into this reaction. Next, let's look at the alkene. Again, you should be able to see two layers. If you can see a yellow tinge, that means that the bromine has not been incorporated into the hydrocarbon. If, however, you see this as colorless, then the bromine has added across the double bond. Looking at the aromatic test tube, same thing. If you can see a yellow tinge to this test tube, then the bromine has not been incorporated. Moving on to the potassium permanganate. The alkane shows this. The permanganate is purple. Moving on to the alkene, the permanganate has been decolored and is now brown, indicating the presence of manganese 4, manganese oxide, instead of permanganate, manganese 7, which is purple. Looking at the aromatic material, there is still purple present in the test tube. For the next set of tests, we're going to place drops of the hydrocarbon into each of these test tubes and then test against sulfuric acid and distilled water. So first, we're going to take the cyclohexane. And then we're going to move on to the other test tubes. Next, we'll add concentrated sulfuric acid to the hydrocarbons. Leave that to stand for a minute and observe what happens. Let's look at the results from these tests. First, sulfuric acid plus alkane appears to be colorless, 2 layers. Next, concentrated sulfuric acid and alkene. Now we know that dilute sulfuric acid plus alkene would make an alcohol, but concentrated sulfuric acid plus an alkene makes a alkyl sulfate. It's responsible for the orangey color right here. If you see brown during an organic reaction, knowing that most organic material is either colorless or ever so slightly yellow, brown is usually an indication of charring because the chemical you've used is a very powerful dehydrating agent, which is the case here with sulfuric acid. If we look at the aromatic, concentrated sulfuric acid will react with aromatics to make a sulfonyl aromatic. And the sulfonyl aromatics are soluble in water. So eventually, this has already started to go cloudy. It is more difficult to discern 2 discrete layers here. Over time, this will become 1 layer. If we look at the physical tests here for density with water, we can see that this test tube is bulk water with a small amount of hydrocarbon floating on the surface. All hydrocarbons are less dense than water. All hydrocarbons are less dense than water. And that is the case with all of them. We've placed some alkane on a watch glass next to some alkene. Now we're going to combust them. And this one. And careful observation will reveal that they burn slightly differently from one another. Can you see the difference? The aftermath of the fire looks like this. This is the watch glass for the alkane. This is the watch glass for the alkene. Can you see the difference?